Hi everybody, and welcome to our next unit, which is on kinetic theory and states of matter. So this is going to be a pretty short unit. It's only 2 sets of notes, and we're going to be talking about our 3 different states of matter. But before we do that, we want to talk about the idea of why do we get these different states of matter? Why do they exist? And what's going on is it's actually a battle between intermolecular forces, all right? Remember, those intermolecular forces are those forces that hold one molecule to another. Things like dipole-dipole forces, London dispersion forces, all right? So it's a battle between intermolecular forces and kinetic energy. All right, kinetic energy is the energy of motion, okay? And all particles are always moving, and we'll talk about that as we go on. And that motion, all right, if it kind of had its choice, if you will, it would have everything being a gas, all right? Because as things are constantly moving, just by random motion, things would be gases. But molecules also have intermolecular forces, and those intermolecular forces tend to hold molecules together. So if you have a situation where the kinetic energy is stronger than those intermolecular forces, you're going to end up getting a gas. If you have the intermolecular forces being stronger than that kinetic energy, you're going to get a liquid or a solid. All right. All of this falls under what is known as kinetic theory. All right, and kinetic theory talks about the impact of temperature and pressure on matter and brings us back to why do we get our states of matter. So kinetic theory, some of it we already know. All matter is composed of small particles, great. These particles are in constant motion, all right? That motion can be rather quick motion, very fast moving around, or it can just be vibrations, okay? But always moving. And then finally, and this one we won't really deal with a whole lot, all collisions between particles are considered perfectly elastic. So while these particles are constantly moving, they're hitting into each other, there really won't be any total change to the kinetic energy before or after a collision. Again, not really something we're going to talk a lot about, but I wanted to make sure you had all 3 tenets of kinetic theory. All right, so let's talk a little bit about gases. We're going to talk very briefly about this because for gases, all right, we actually are going to have 2 whole units on gases coming up in the coming up after this unit. All right, so as I mentioned before, for gases, what we have are very weak intermolecular forces. All right, therefore the kinetic energy wins, and you have these particles that are going to move as far away from each other as the container will allow. Now, this brings us to the idea of volume and shape. Gases have no set volume or shape. They will take the shape and the volume of whatever container that they are in. All right. Because of this, we really need to know more about gases. And there's 2 things about gases you always need to be aware of, and those are pressure and temperature. And that's what we're going to spend the rest of this unit talking about. All right. So what is pressure? Well, pressure is force, okay, per unit area. So what does that mean? Well, it's the amount of force exerted over a certain amount of area, and that is what pressure is. What we're mainly interested in is gas pressure, sometimes known as vapor pressure. All right, and this is the force exerted by a gas on the walls of its container. All right, the tool used to measure pressure is known as a manometer. And there's several types of manometers out there. One that most likely you have heard of before is a barometer. All right, and a barometer measures air pressure, and that's why on the news when they're talking about the weather, they'll talk about the barometric pressure. All right, so the barometer is used for air pressure. Okay, another type of pressure that you guys have all experienced before as far as an instrument is what measures blood pressure. And if you want to look that one up, it's a really fun word. It is my favorite type of manometer, but I will leave that a mystery for you, and you can look that up and see what that one is. All right, so let's talk about some of the units that you're going to be using when dealing with pressure. And you are going to need to know these units and be able to convert between them. So the SI unit is the Pascal All right, and we are going to actually be using the kilopascal because this is a very small unit. So we're going to use, and it's kPa like that, it's a little k, capital P, and a lowercase a. All right, this one is used a lot. Our textbook uses kilopascal, so we tend to use that one a lot. There's also what is known as atmospheres, all right, and this is known as standard atmospheric pressure, and this is an ATM, okay, and then finally, we have the oldest unit, and sorry, this is kind of out of order, your oldest unit, which is known as a millimeter of mercury, or mmHg. All right, so the conversion you need to remember is this. 1 atmosphere is the same as 101.3 kilopascals, which is the same as 760 millimeters of mercury. You must know these. You're going to be asked a lot of questions asking you to convert back and forth between these units. And not only in this unit are you going to be asked those questions, but also in our gas units that are coming up. All right, so let's take a really quick look at these sample problems, okay? And I'll just leave those conversions right there for us to see. So what pressure in kilopascals and atmospheres does a gas exert at 385 millimeters of mercury? I'm doing a conversion. I am going to use factor label because it is the best way to do conversions. So 385 mmHg. I want to get rid of that, and we'll first go to kilopascals. All right, so I'm going to put kPa at the top. I'm going to get rid of millimeters of mercury, so they're going to go at the bottom. Here are my conversion units. So 760 goes with millimeters of mercury, and 101.3 goes with kilopascals. All right. All of these, by the way, are what are known as standard atmospheric pressure. And what that means when we're talking about standard pressure, that is typically air pressure on a really sunny day at sea level. That's what's been decided that what standard pressure is going to be. So where we live, all right outside of Washington, D.C., where we live, we are just about at sea level. So on a sunny day, our air pressure is going to be right around these numbers. Okay, so let's go back to our problem. So we're just going to take that 385, we're going to multiply it by 101.3, divide it by 760, and you should get about 51.3 kPa. Okay, we're going to do the same now, except for now, we're going to take that millimeters of mercury and we're going to convert it to atmospheres. All right, so 760 mmHg goes at the bottom. 1 atmosphere goes at the top. All right, and again, you're going to take your calculators out, and 385 divided by 760, and that's going to give you about 0.507. Okay, is it 0.507? I'll write that a little bit neater for everybody. Okay, 507, and that is in atmospheres. So nice and easy. All right, you can go on ahead if you'd like to pause the video and do the next one on your own, or you can just go on ahead and watch me do it. All right, the pressure at the top of Mount Everest is 33.7 kilopascals. Is that pressure greater or less than 0.25 atmospheres? Well, there's a couple ways that you could solve this. You could convert atmospheres to kilopascals, or I'll just go ahead and do those kilopascals to atmospheres. All right, so 33.7 kPa. All right, I want to get rid of kPa, so they go on the bottom. I want to go to atmospheres, so that's going to go on the top. 1 atmosphere is equivalent to 101.3 kPa. When you divide this out, you get about 0.33 atmospheres. All right, so this pressure is greater than 0.25. So again, we're going to ask a bunch of questions just for you to practice, but this is going to be a skill you're going to be using over the next several weeks of converting your pressure units. So be ready for that. All right, so we're going to finish up today talking about temperature. Okay, and temperature is defined as the measure of the average kinetic energy of a substance. All right, and kinetic energy, what kinetic energy actually is, as far as the equation, we're not going to be mathematically using this, but just so you know, it's 1/2 mass times velocity squared. And those of you who have taken physics or are in physics now certainly have experienced this equation before. All right, but what we really are taking from this is, so what is temperature dealing with? Well, temperature is dealing with the mass of the substance, okay, that you're talking about, and how fast it's going. All right, so if you have something that has a higher mass, it doesn't need to be going as fast to have the same temperature as something with a lower mass, which is going to need to be moving faster. All right, so really the takeaway, temperature deals with the mass and how quickly, the velocity that a particular substance is moving. Okay, all right, since temperature is a measure of the average kinetic energy, and kinetic energy is the energy of motion, what's going to happen as particles slow down? Well, as particles slow down, your temperature is going to go down. What if the particles stopped moving? Now, this is a theoretical situation because we know, according to kinetic theory, that particles are always in motion, but they can be going very, very slow. And theoretically, when particles stop moving, we reach what is known as absolute zero, the temperature at which motion of particles theoretically stops. All right, absolute zero is what the Kelvin scale is based on. And the Kelvin scale is a scale for temperature that we use quite a bit, and we use exclusively for gas laws, because what's nice about it is we're never going to have the number or the value zero, all right, because 0 Kelvin is absolute zero, and we can't get that low. It doesn't exist. We can get very close, but not there. And we will never be dealing with negative numbers. All right, so that's going to help as we deal with calculations as we go forward. All right, so what is absolute zero? Well, absolute zero is negative 273.15 degrees Celsius. All right, we're just going to round that to negative 273 because we're going to be using this number so much. That is what 0 Kelvin is. Now, we use Kelvin in calculations, but when we take temperatures using a thermometer, that's going to always be in Celsius. So you're going to need to be able to convert from Celsius to Kelvin, all right, quite a bit. You're going to need to do that all of the time. So let's take a look at a nice simple example. At what temperature in Kelvin does water freeze? All right, well, we need to know first Celsius, and we should know this, that water freezes, okay, so freezes at, I don't know why I just drew that, at 0 degrees Celsius. Well, what is that Kelvin? You're just going to simply add 273 to that number. So plus 273, that gives us 273 Kelvin. That's the temperature at which water freezes. All right, or ice melts, however you want to think of it. All right, well, what about boil? Well, water boils at 100 degrees Celsius. So again, I'm just going to add 273. Very straightforward. And it's a super easy conversion, which is really nice. So the boiling point of water in Kelvin is 373. All right, this conversion is so easy because a change in degree for Celsius and for Kelvin, it is the same. All right, and these scales were developed, the Kelvin scale was developed to use with the Celsius scale, so it is nice and straightforward. All right, so we're going to be doing some practice with this. Have a great day, everybody.